Yeah. So how was quiz 2?
Was mixed actually for me.
No, in general, like for everybody, how was it?
Pardon me, ma'am, can't hear you completely properly.
You did it properly?
Your voice is not very clear.
No, I was asking like in general, how was quiz 2 for everybody?
Yeah, it was mixed for me actually. I did some silly mistakes.
Okay. What about others? Ayush Sharma said it's good. Okay. So paper was not lengthy, not difficult, right?
Yeah, yes, ma'am.
Okay.
Ma'am, I found it a bit lengthy.
Oh, you found it a bit lengthy? Okay. Section, okay.
I don't know, maybe I just got
okay. Somebody else is also saying it was lengthy.
Yeah, even for me, I couldn't complete it in time actually.
Okay.
Ma'am, there was a question based on MGF, but in the solution, the answer is wrong, ma'am, I think.
Yeah,
Yes,
we saw. Yeah, that all will be rectified. We'll correct it from our side.
More questions, ma'am. Ma'am, there are a couple of more questions. Their sequencing is, I think, is wrong. Sequencing is wrong.
Okay, you
like
had posted something about
probability, na? For question number 3, where the answer is that fxy of xy is 1 by 5.
Okay.
So in QPV1 question said this option was at number 4, right? But in the answer key, this option.
I need to check. I need to check that question. I'm not sure if that is wrong. I need to check.
No, ma'am. Maybe it's just the ordering of the answer in the sheet that is provided on the portal, and the one actually that was present in the exam. But I think that's okay. It's just the ordering that is.
Ma'am, am I audible?
Yes, you are audible. You are audible.
Yeah. I was saying something. I think I got disconnected in between.
No, I know you had posted event on Discourse. I need to check that.
Right. You got it now. What I'm trying to say, because I got disconnected in between. The ordering is wrong in the answer key.
Ordering is wrong, or the correct answer is wrong.
Yes, of the options. The correct answer, for that question is one of the correct answer is 1 by 5 when xy belongs to D, right? Because the total area is 5, so the PDF will be 1 by 5, right?
Okay, yeah.
So this option during the exam set QPB1 was at number 4. But in the
you mean the correct option was something correct option?
Answer is correct, ma'am. There is nothing wrong in answer, but the sequencing of the option is wrong.
So yeah, like you will get shuffled question, like shuffled options.
But my set was QPB1, and I'm talking about the response sheet of QPB1 only.
Okay, we'll check. If it is wrong, if something is wrong, it will be rectified. No issues. Okay. So let's start the session now. I will share my screen. Okay, so how many of you have studied week 5?
Week 5?
Oh, sorry, not week 5, week 10.
Not started, ma'am.
Not started?
Yes, ma'am, I have studied it.
So how many, can you raise your hand, how many of you have gone through week?
I'm gone through a couple of videos, finding it a bit difficult.
Ma'am, I could do only half of it.
Okay, half of it, okay. Four people. Only 4 people have watched the lectures yet or started watching it.
मैम क्विज 2 था
Yeah, I know.
एंड एक्चुअली मैथ स्टार्ट किया उसके बाद इसके लिए अभी तक स्टैट्स नहीं हुए
Okay. Okay, I could see some 6, 7 people. All right. So what did you understand? Like, even though when you started, what did you understand from this week? Any idea?
Different ways to calculate p hat basically.
Ma'am, this is a real-time estimation, what I feel like real-time situations kind of thing. So
Okay.
how we can derive the conclusion based on the probability, based on the given data, I mean the prior thing and all. I think that is a thing. I think this is what we're going to use in real time also, ma'am. This is what I feel from this thing.
Okay.
But ma'am,
anybody else? Huh?
very difficult for me, ma'am. I didn't understand completely. Kind of, so I just need a little push from here.
Okay. Okay. So are you a working professional? Yeah.
Yes, ma'am.
Okay.
Yes, ma'am. I'm working professional, so that's why. But still, I tried a lot. I went through up to three lectures. Okay, but I felt little, and I can't understand the what sir is teaching over there. So I'm just looking here and there the YouTube video and different references I'm trying to use. But still, I just need a little more explanation actually. So that will be good for me. The basics kind of thing.
Okay. Yeah. Somebody else was saying something.
Ma'am, I said different ways to calculate p hat basically.
Okay. Okay. All right. Okay, so in week 9, like it's mostly the extension from week 9. So what we were seeing in week 9 was like you have some IID samples coming from some particular distribution, and we wanted to estimate the parameter of the distribution of X, right? So in week 9, we saw some random samples you have, and they're coming from particular distribution with some, let's say, some parameter theta. And we were trying to estimate this parameter, right? We were trying to estimate this parameter theta. So in there, what we had studied was like this parameter theta. So what is this? This is parameter. So this parameter theta was the constant. Was the constant in week 9, right? Where we also studied 2 ways to design the estimator. So one we studied that was method of moments, and the other was the maximum likelihood. Right. So these 2 methods we have, like these 2 ways we had studied in week 9, through which we can design our estimator, right? Now, in this week, what we are doing is like instead of assuming this parameter theta to be a constant, what we are saying is that this parameter theta is a random variable. It is no more a constant. We are saying that this is a random variable. And since this is a random variable, you know that if you have any random variable, that random variable is going to have some distribution. So what we are saying is like this parameter theta is a random variable. And it has some distribution. Let's say the distribution of this theta is f theta of theta. So in place of, we'll write a capital theta. So let's denote this as capital theta. Okay. So we are saying this capital theta is a random variable. All right. And it has some particular distribution that we have denoted using f theta of theta. So this is a major difference that is there in week 9 and week 10. So there we were looking at the cases where okay, so the first case, this one, right? This we call it as frequentist approach. Frequentist approach. So we are trying to estimate our parameter where we are assuming our parameter to be constant. So this kind of thought process, this way of doing it, we call it as frequentist approach. And this method is called the Bayesian approach. Here also we are trying to estimate our parameter, but in place of assuming that our parameter is a constant, what we are saying is that this parameter is no more a constant, it is a random variable. And since it is a random variable, it is going to have some distribution. Okay. So till now, is it clear? Like, are you able to understand what's the difference?
Yeah.
Yes, ma'am.
Yes, ma'am.
So this is a
Yes.
major difference that we are going to see in week 9 and week 10. Now, okay. So we'll just put a regular setting here. So we are saying that x1, x2 up to xn is a random sample and they are IID and they are coming from some x, okay? And this x has some distribution, okay? Let's say first this has a particular parameter. This is a parameter theta. This x has a parameter theta, okay? And this parameter now is a random variable. And this particular theta has a distribution and we are denoting it as f theta of theta. So the first thing that you must have seen in the lecture is that we have a particular setting and where we are saying that you have a random sample x1 to xn coming from a Bernoulli P distribution, okay? But here this P is no more a constant, this is a random variable, okay? So I will just write it as bold P, right? So this is a random variable. Now, since it's a random variable, we are saying that this is going to have some distribution. So we are assuming that this P, this cap bold P, is coming from a uniform distribution where it can be either 0.25 or it can be 0.75, right? Also, sir had explained in the lecture, like basically it is a you have to urn and you have some marble in the urn and you pick a coin or you pick an urn and what is the probability of that you'll get, what is the probability of getting that marble, right? So something of this setting we have here. So you have, this random variable P and this has a distribution that is uniform 0.25 and 0.75. So what we're doing is we just observe the sample. So let's say if we have a coin, like since the Bernoulli distribution, let's say it is a coin toss problem, and we pick a coin. We don't know which urn it is coming from or what is the distribution of this P. Either it is coming from a distribution where P is 0.25 or it is 0.75. We don't know that. We just pick a coin and we noted down few of the sample like the realization of the random variable. So let's say I pick a sample that is giving me, let's say 10101. Okay. So what does it mean? So it means you had 5 samples, x1, x2, x3, x4, x5, and these are the values that it takes. So x1 equals 0, x2 equals 0. Sorry, here it is 1. X1 is 1, right? So x1 equal 1, x2 equals 0, x3 equal 1, x4 equals 0, and x5 equal 1. So this is the setting we have, right? This is the sample you observed, and now you want to find out, like, what is the probability that this P is 0.75 given this sample. So what can we write this as? Any idea what should we write? It is a kind of base problem.
P of S given P equal to 0.75
Yes.
Into P of 0.75 divided
Yes.
by P of S.
Divided by P of S. And what should we write the P of S as?
It should be
Summation, ma'am.
yeah, summation. Yeah.
Summation, right?
Yeah.
So sum over probability that S given P equal sum P. I will write this as bold P. Okay. And P is okay. Instead of writing this, I can quickly write this. So let's write here 0.75 P of 0.75 and plus probability S given P equal 0.25 times probability P equal 0.25, right? This is going to be P of S.
Yeah.
So you know what is P of 0.75, because since this P is a uniform, what we know is this P is a uniform random variable and it has an equal chance of either getting a 0.25 or 0.75. So this is going to be half, right? And given this sample, given this P equal 0.75, what is the probability of occurrence of this capital S? So let's try to find it here. So what is the probability of the occurrence of this sample given P equal 0.75? So what do we mean by this?
Probability of S when P is 0.75.
Yes. So what it should be?
0.75 into 0.25 into 0.75.
Yes.
3 times 0.75.
Yes. So basically 0.75 to the power
3.
And 0.25 to the power 2, right? This is the probability of occurrence of this sample given that this P is 0.75, right? So what we did is we found probability, let's write it as PR, probability that this random variable P is taking the value 0.75 given this sample, and we found the probability that this random variable P is taking the value 0.25 given the sample, right? So after this, we have designed 2 estimators, right? So one estimator was posterior mode and the other one was posterior mean. So in posterior mode, what we are doing is we are just looking at which probability is more, like which probability is more, like given this sample, given this, you have observed this sample, like which probability is coming out to be greater. So whatever comes out to be greater, we'll say that this coin is coming from this particular distribution, right? So let's say if probability P equal 0.75 given this S, if this comes out to be greater than this probability, then we will say the posterior mode is 0.75, P equal 0.75 if this comes greater. But if probability P equal 0.25 comes to be greater, we'll say the posterior mode is 0.25. So this is what we are doing in when the estimator is mode. But in case we have the estimator to be mean, in that case, we are just, so in general, how do you find the mean, right? So you just do x times fx of x, right? So I varying from I 1 to 1. Okay. So you take whatever values the random variable is taking, you take the value and the probability of occurrence of that value. So this you sum it over for all the random variable, right? All the values that the random variable takes. So here, what is the random variable we have? The random variable here is this P, bold P. So while finding the posterior mean, what we are doing is we are just taking this P. So here P is taking 2 values. One is 0.25, another is 0.75. So there is something called conditional expectation. I don't think we have read about this in this course. So it is nothing much. You just have like the random variable p is taking the value 0.25, and you're just multiplying this with in place of probability of this 0.25, you are multiplying this with the conditional probability. So this is going to be probability p equals 0.25 given s, plus you have the random variable taking the value 0.75, and you multiply it with the conditional probability p equal 0.75 given the s. Okay, so this is what we get as posterior mean. So the posterior mean is kind of this estimator is kind of a little better than the posterior mode. It gives a kind of, it averages out the values whatever we takes. So generally we use this posterior mean as our estimator. Throughout this course also, in week 10, we'll be using the posterior mean as our estimator, like the Bayesian estimator. Okay, so this is what we are going to use in this whole week. How to find the posterior mean basically. So this, how to calculate this posterior mean or estimator. Okay, so any doubt till here? Like, are you getting what we are trying to do here?
Yes, ma'am.
So,
ma'am, can you just quickly once explain the posterior mean mode briefly, ma'am, if it's possible?
posterior mean and mode.
Yes, ma'am.
Okay. So in posterior mode, what we saw is like we had calculated the probability of like what is the probability that given this sample, what is the probability that this random variable p is going to take the value 0.75. Then we also calculated what is the probability that this random variable given this sample, what is the probability that this random variable is going to take the value 0.25, right? So whatever comes to be maximum, right? So whatever comes, whichever probability comes out to be maximum, we generally say, okay, this is our posterior mode, and so I will take this as my estimator. Okay, but in posterior mean, what we are doing it, like we are just averaging out. So whatever values your p is taking, so 0.25, and whatever the conditional probability of 0.25 is. So here we don't have the actual probability, like what is the probability that p equal 0.2. So okay, we have the actual probability too, but since we have observed the sample, and this probability is going to be dependent on the sample that we have observed. So in place of the actual probability of 0.25, we are like taking the conditional probability. Like given this sample, what is the probability that your p is 0.25? And then the other random variable, then p is also taking the value 0.75. So you will take 0.75 times probability that p equal 0.75 given the sample. And then you find the average, the general way you find the average, we're just doing this. And you will see that it will give a slightly better, it gives a slightly better result than the posterior mode. So throughout this whole week, we are going to use our estimator as posterior mean. Like whatever example you will see, right? Basically, we are going to deal with posterior mean as an estimator.
Ma'am, when you say better results in posterior mode, what do you mean by that? Better results?
Sorry?
Ma'am, what do you mean by better results? Yeah.
Okay, so I haven't calculated here properly, and I'm not sure if this is the example that was taken in the lecture, but just let me see once. So 10110 and here it is 0.625. Okay. So, okay, let's say this was the sample we had, and the posterior mode had come out to be 0.75. Okay, I'll just write it on a different page. See, I had said x1 to xn was coming from Bernoulli distribution. Okay, and this P has a uniform distribution, 25 and 75. We observed the sample. Let's say the sample was 10110. And then we found posterior mode that came out to be 0.75. And we found posterior mean that came out to be 0.625. So you look at this sample, okay? So like out of 5 times, 3 times you are getting the head. So this is kind of more close to 0.6, right? Probability of getting a head is kind of more close to 0.6. So by using the posterior mean, we are getting a better, like this seems more reasonable, right? Than 0.75.
So is that generally the case? Posterior means coming out better than the posterior mode.
Sorry, can you repeat?
I'm saying that is that a general case then, ma'am? Posterior means always come out better than posterior mode, gives a better estimation.
Yes, it mostly in most of the cases, yeah, it comes out to be like that.
Okay,
so
thank you.
is, yeah, like both of them are estimator, but we are saying that this gives a slightly reasonable result. So we are going to use this estimator in this whole week. Okay.
Have we discussed how to calculate posterior?
Yes, we are doing it now. So the general setting that that we are going to have for this week is, like for the Bayesian approach, is you have an IID sample from X, and let's say this distribution X has a parameter theta. Okay, this is a random variable, and this theta has a distribution. We are saying it is f theta. And we have observed the sample that is x1 equal x1, x2 equal small x2, up to xn equal small xn, right? So we always say that posterior is proportional to likelihood times prior. So likelihood we have seen in the previous week, right? And this prior is this prior, like whatever prior information you have about the parameter. Okay. So in this case, this parameter theta is a random variable. So it is going to have some distribution. So we are calling it this as prior distribution. So we are denoting the prior distribution as f theta of theta. So this is the prior distribution of theta. Okay. Prior distribution. Now, what is likelihood? Likelihood is like what is the probability of occurrence of this sample? So what is the probability that x1 is going to be x1, x2 is going to be x2, up to xn is going to be xn, given this theta, given this parameter theta is our small theta. Okay, so what is this. So this is your likelihood given some information about the parameter. What is the probability of occurrence of this sample? And the prior is again, you have f theta of theta. This is basically your sample, and posterior is going to be probability of theta equal theta given this S, right? So this is the general Bayesian setting we are going to have. Okay, so let's look at one problem first. We'll take the first example. So okay. Let's see one example here. So how do you find the posterior actually? How do you find the posterior distribution? Now, the very first example that you have is let x1, x2 up to xn is IID Bernoulli P. Okay. And this P, we are saying the distribution of this P is uniform 0, 1. Okay. So this is the prior distribution of the parameter P. Now you want to find the posterior. You want to find the posterior. So you want to find what is the probability. What is the probability that this P, so wait. So this P, right? This P equal to some small p given the sample. So this is directly going to be product of this likelihood times prior. So what is the prior distribution here? What is the prior distribution here?
The uniform one, uniform 0,
Uniform 0, 1, right? So what is the distribution of this? I mean, the distribution is
Continuous.
no, I mean the distribution is 1. What is the PDF basically? This is PDF, right?
1, no? 1, ma'am.
1, right? So this is going to be proportional to, I will first write prior. So it is going to be 1. And what is likelihood? Likelihood is simply probability that x1 equal x1 up to xn equal xn given this p equal the small p. Okay. So, okay. So how can you write this probability?
By
So multiplying each probability, ma'am, because yes. So basically we are trying to find what is the probability that your x1 is taking the value x1, x2 is taking the value x2 up to xn. And you know that these samples are coming from a Bernoulli P distribution, Bernoulli distribution. So it is either going to all of these small xi's. So they're either going to take the value 1 or they're going to take the value 0, correct?
Yes, ma'am.
So let's say in the sample, your W represent, let's say your W represent number of ones in the sample. And since you have a sample of size n, so n minus W is going to represent, what is it going to represent?
Number of zeros.
Number of zeros in the sample, right? So what we are saying is we are assuming that this P, this random variable P is going to take the value small p, right? So once you write the probability for like a Bernoulli setting, in a Bernoulli setting, then in that case, I'm just saying that P is occurring. I mean, 1 is occurring. Okay, before that we'll say, like if if X is a Bernoulli distribution, Bernoulli, let's say Bernoulli 0.5 distribution, okay. So what is the probability that X equal 1? It is 0.5.
Yes.
What is the probability that X equals 0? It is 0.5, right? Because here its P was 0, like 0.5. So, but here we don't know what the P is. What can we write probability like X1 equal X1, like capital X1 equal X, small x1. It can be anything, right? So let's say 1 occurred W times in the sample and 0 occurred N minus W times in the sample. So if 1 is occurring W times in the sample, so we are going to write this as P to the power W, right? If W is occurring, if 1 is occurring W times in the sample, then we are going to write like P to the power W. And if 0 is occurring N minus W times in the sample, we are going to write it as 1 minus P to the power N minus W, right?
Yes.
Right. So this is what we have written here. So P to the power W, it means number of times your W occurred in the sample, and 1 minus P. So this is, what is P? This P is probability of success. And what is this 1 minus P? This is probability of failure, right? So since we did not know what the P is, since it's a random variable, we are just saying, let's say it is W time that 1 had occurred in the sample, and it is N minus W time that 0 has occurred in the sample. So we can write this as P to the power W and 1 minus P to the power N minus W. Is it fine?
Yes, ma'am.
Right. Now, so what we're saying is that the posterior is proportional to P to the power W, 1 minus P to the power N minus W, right? This is what we got. So looking at this, can you say anything about what kind of distribution it is? Any guesses?
Resembles gamma, beta.
It is kind of beta distribution. So if you look at beta distribution, if I'm saying the random variable X is following a beta distribution with the parameter alpha and beta, then its PDF fx of X is given is something of the kind X to the power alpha minus 1, 1 minus X to the power beta minus 1, right? This is how it looks like.
Yes.
Right. So here also, just in place of X, we have P. Since here X was a random variable, but here P is a random variable. So in place of X, we have P. And in place of alpha minus 1, okay, see, in place of alpha minus 1, we have W, right? And in place of beta minus 1, we have N minus W, right? So if X, this we have written it as beta alpha comma beta, right? So if we have something of this kind, how can we write this in beta distribution? What is going to be the parameter alpha here?
W plus
W
1.
plus 1.
Sorry, can you repeat again?
Alpha is W plus 1.
W plus 1, right? And what is going to be beta here?
N minus W.
N minus W plus 1.
N minus W plus 1. So from where we found out that the posterior is something proportional to, it's kind of a beta distribution. This is what we found, that the parameter is basically something of the beta distribution. And as we are assuming, so we are going to take the estimator, that is posterior mean, right? So since we know the distribution for posterior, so the posterior distribution came out to be something of beta, where the parameter alpha was W minus 1, right? W plus 1. And the parameter beta was N minus W plus 1. Okay. So this is how the posterior distribution is. And we wanted to estimate, in this case, the parameter P. And to estimate this parameter P, we are going to use this. So this is a parameter. To estimate this parameter P, we are going to use the estimator, that is posterior mean. So once you know what the distribution of posterior is, can you find the posterior mean? So what if the posterior is beta, what is going to be the posterior mean?
Mean of this beta distribution.
Yeah. Alpha
so-
divided by alpha plus beta.
Alpha upon alpha plus beta,
Yes, ma'am.
right? So it is going to be W plus 1 divided by W plus 1 plus N minus W plus 1. So this is going to get cancelled out, and we are going to get W plus 1 divided by N plus 2. Right?
Yes, ma'am.
So this is what we are doing here. This was a very basic, simple example. So where we had taken the prior to be uniform 0, 1. Okay. Now we can have like this was the prior was very simple, where we had just taken this prior to be uniform 0, 1. Now this prior can be different. So what we have seen is if we take the prior to be beta distribution only, let's say what we are saying is the samples are coming from the Bernoulli P distribution, and the prior distribution is the distribution of the parameter, what we know is coming from beta distribution. So once you do that, like if you take the prior to be beta distribution, beta alpha comma beta, then the posterior also comes out to be some beta distribution. Okay, let's say the parameter is A comma B. So such kind of cases we call it as conjugate priors, right? So what like if the prior is the same, if the distribution of prior if the distribution of posterior comes out to be the same as the distribution of prior, such cases, such priors are called conjugate priors. Such cases are called conjugate priors. Okay.
Here, how does one estimate these parameters alpha and beta for this distribution?
This distribution?
Yes, for the prior distribution.
How do you estimate the parameter alpha beta?
So like this is a double estimation problem when you use Bayesian.
You don't want to estimate the like what is alpha and beta here. We are just saying that we have only this prior information about the parameter P, like if the samples are coming from the Bernoulli P. Okay, what we are just saying is this P has some beta distribution. We don't know what is this parameter alpha, what is this parameter beta.
Okay, I see.
Or maybe if we know also, like let's say we know what is alpha beta. So our goal is not to not what is alpha and beta. It maybe you already know. You can just say something here. Our goal is to estimate the parameter P. Right? Posterior is probability of this P given the sample.
Ma'am, but in the final expression for the estimator P, alpha and beta also shows up now. So we need to know.
So you will know, like this distribution you will know. Like let's say you know this is this distribution.
Okay, it's already given.
Yeah, like you have some prior knowledge about this parameter, and here in this case we are saying that this, let's say this what we know is that this parameter is following the beta distribution that has some alpha and some beta. Okay. It can be any number. Let's say it is beta 1, 2. Let's say I know that this P is beta 1, 2. Okay.
Ma'am, prior will always be known, right?
Prior will always be known. That is what prior is. I mean, something that you know from before. Right?
Ma'am, one question here. Sorry, I misinterpreted here. So, see, the question was about the Bernoulli the distribution, right? So, in the prior thing you have choose from the uniform distribution kind of thing, probably. So, I mean, what is the use actually? Like, what is the significance of the Bernoulli distribution and the uniform distribution, ma'am? How they play the role in finding the prior, ma'am? I mean, in the posterior distribution, ma'am. What is the role of Bernoulli? Okay, and what is the role of the uniform distribution, ma'am?
What is the role of Bernoulli and what is the role
Yes.
of uniform distribution?
Yeah. Yes, ma'am.
So, okay, it is very messy.
Since it was a Bernoulli, so you have used the formula. Okay, how many ones are there, and the W and minus W.
Yeah, so it is not necessary that your samples like X1, these samples come from Bernoulli P distribution. It is not necessary, right? It can be anything, any distribution. But we don't know we just know it is coming from particular distribution. But let's say we don't know what this parameter P is. But what we know is, since this is a random variable, from our prior information, like we had some prior information, and we are just saying that this had some distribution, some prior distribution. And in the first case, we had said, like, we had assumed, like, our prior knowledge about this parameter P, that is the random variable, is that this follows a uniform 0-1 distribution. In the second case, what we are saying is, let's say what we know is from our prior knowledge that this P has some beta distribution. And on the basis of what the prior knowledge do we have, on the basis of that, we are trying to find a posterior distribution. And once we find what the posterior distribution is, it's easy for us to find the estimator for the parameter.
Okay, ma'am.
Yeah. So how do you find? Okay, okay, that was not the problem. So you can try doing this. It has been done in lecture. So can you try to do it now? Like, the setting is same. I mean, you have the random sample coming from a Bernoulli P distribution. In place of a uniform 0-1, now your prior is this is a prior information. The prior distribution is, in place of uniform 0-1, you have beta, alpha, comma beta. Okay. So what is the posterior? Can you try it out now? I will just give you 2 minutes. Just try to do it on yourself. So the way we had done the previous problem, this problem, right? This problem over here. The same way you can try for this setting. Can you do it now? Yes, no?
Yes, ma'am. We have to consider X1 to Xn as Bernoulli only, right?
Yes, the same problem. I'm just changing the prior here.
Okay.
Yeah. Yeah, this has been done in lecture, but it's better you try it on once. Okay. I'll just give you 2 minutes.
Ma'am, can you show the previous page, ma'am? Can you show the previous page?
Yes. Yeah. So I can write it here only. You take the prior to be beta AB. Okay. Write it clearly. Take prior to be beta A comma B. Is it done?
Yes, ma'am.
Okay, so what is the posterior that you are getting?
Beta with parameters alpha plus w and beta plus n minus w.
Yeah, tell me. Beta
with first parameter is alpha plus w and second one is beta plus n minus w.
Beta plus n minus w. Okay. Who else got this? Anybody else who got this? Okay, so Deep Kevin has got the same answer.
I may be mistaken, but I seem to have gotten alpha as n plus alpha, n plus, yeah. The beta distribution is going by alpha. I got it as n plus alpha.
Oh, sorry. Can you repeat again? You're getting alpha to be
N plus alpha.
N plus alpha. Okay. And
on beta was x1 plus x2 till xn minus n plus beta.
Plus
Beta minus n. No, minus n plus beta.
Minus n
plus
beta. Okay.
I'm not sure that is the correct one.
Okay. Okay. Sorry. Anybody else who got something? No one? Okay, let's see which one is correct. Okay. I will do it here. So we had the samples coming from the Bernoulli P distribution. We knew the P is uniform, sorry, P is beta, alpha, comma, beta. Now the posterior is proportional to likelihood times prior, likelihood times prior. And the prior was probability x1 equal x1 up to xn equal xn, given this P equals small p, okay, times prior. And the prior distribution here we have as beta, alpha, comma, beta. So we know the distribution is for P basically is going to be, I will just write it here. So P, okay. So this is nothing but again P to the power W 1 minus P to the power n minus W for the likelihood. It is going to be same as the previous one. But in the prior distribution, this is going to change here. So here it is going to be x to the power alpha minus 1, right? So it is P to the power alpha minus 1, 1 minus P to the power beta minus 1, right? This is a distribution. So x to the power alpha minus 1, 1 minus P to the power beta minus 1. So this P we can write it combined. So P to the power W plus alpha minus 1 times 1 minus P to the power n minus W plus beta minus 1. So again, this is kind of a beta distribution, right? But what is the parameter alpha here? So parameter alpha is going to be W plus alpha, right? W plus alpha. And the parameter beta is going to be n minus W plus beta. So the first one here is correct. Did you get, how did we get beta w plus alpha and minus w plus beta?
Ma'am, I have not understood about that w plus alpha minus 1, ma'am. Where that minus 1 goes?
Okay, so, okay, let's see. This is what we got, right?
Yes, ma'am, I have understood till there. Yeah.
So if X is a beta distribution with the parameter a comma b, then fx of x is written as x to the power a minus 1 minus x to the power b minus 1. Okay.
Okay. Now comparing those two, ma'am.
Yeah. So here you have
minus 1 minus 1.
w plus alpha minus 1. So the parameter a is going to be w plus alpha, and the parameter b is going to be n minus w plus beta. Correct? Just compare these two.
Okay, ma'am. Okay.
So since you saw here that even the prior you had taken as beta and the posterior also you got it as beta. So such kind of prior is called as conjugate prior. Any doubt in understanding how did we reach at the final answer? Like the whole week, this whole week we are going to do the same thing. It's like different distributions, different priors.
Ma'am, I understood this thing. Can you this problem actually? Can you just draw the graphically, ma'am? How will the distribution will look like when we say is a Bernoulli P and distribution is like beta is a prior. So in graphically, how will you describe this thing, this problem, ma'am? Can you just show me?
Graphically, okay.
Yeah, it's a rough thing is fine. I mean, so when you say the x1, x1, x2 is a Bernoulli. Okay, and this prior is following the beta distribution. Yeah, so how actually it look like, ma'am? The problem actually, ma'am. I just want to understand that thing.
How does the problem look like?
Yeah, graphically, ma'am. Graphically, can you just draw a graph? Okay, this is how, like a normal distribution, right? It looked like this thing. So how are we relating the Bernoulli and the beta relation, ma'am? This is what I want to know.
Okay. The
Yeah, randomly you choose as a beta as a prior as a beta, and you can take anything, right? So in this problem, okay, this is the Bernoulli, all the variables are, this is a Bernoulli distribution. Okay, the prior is following the beta kind of distribution. How they are related, ma'am?
Okay, wait, I can refer you to some graphs. Wait, just give me a minute. Okay, so there is a book. Okay, you can write it down also. So Can I write the name of the book here? You can refer to this book for a better understanding of Bayesian estimation. There you have a lot of graphs and pictures. Right. I will write it in chat box. Okay. So the name of the book is Intro to Bayesian Statistics. I can... Wait. Are you able to see this?
Yes, ma'am. We can see. I can see.
Yeah. So this is from a book that is Intro to Bayesian Statistics. You can refer to this book actually. So see, here you had like there are three different people and they had taken three different priors and their priors have been sketched here. And on the basis of the prior, they are getting the posterior distribution. So we can.
Ma'am, who is the author, ma'am?
I will put it in chat box. Okay.
So, and my sincere apology for to all the students. I took a lot of time actually. So.
No, it's fine. Like if you're interested in Bayesian part, this is a good book to refer. This by in place of intro, it is introduction. Introduction to Bayesian statistics. Yeah, I have put it in chat box. You can check. You can check in the chat box, okay? Am I audible?
Yes, ma'am.
Yeah. Okay. All right. So we can move to the next problem. So whatever we just did, the same thing we are going to do throughout. Just the samples will be coming from some different distribution. We'll have some parameter and that parameter is going to have some distribution. And on the basis of that, we are going to find the posterior. So the next problem that we have in this lecture is the samples coming from a normal distribution where your variance is known, but the mean is unknown. Like the mean is a parameter that is unknown and this is some random variable m. And that random variable also is a normal, like we are assuming is that the prior information about that random variable that random variable is also normal with some mu and some sigma. Okay. So how are we going to do this? Has anyone tried this?
I tried in from the activity thing, but I got it wrong, ma'am.
Okay, let's see. Let's try to do it here. So we have the samples x1, x2 up to xn. We are saying it is coming from normal m with sigma square. So here we are saying that the sigma square is known to us, but this capital M, that is our mu, is unknown. Okay, so this mean is unknown, and it has also some distribution that is also normal with mean mu naught and variance sigma naught square. So what is going to be the posterior distribution of this capital M? So the first thing is, okay, so the first thing I will do is, what is the prior distribution of M? The prior is mu naught sigma naught square. It is again normal, so it is going to follow. So let's write it like this. This is going to be 1 upon sigma naught, 1 upon sigma naught under root 2 pi, right? E to the power minus 1 upon 2 m minus mu naught upon sigma naught whole square, right? This is our prior distribution. This is right.
Yes, ma'am.
Yeah. Okay. So the posterior is going to be prior times likelihood. Prior we can write it from here. So it is 1 upon sigma naught under root 2 pi e to the power minus 1 upon 2 m minus mu naught upon sigma naught square, right? This is our prior. Times the likelihood is going to be probability that x1 equal x1 up to xn equal xn, given that this m is a normal, m is coming from the normal distribution. So let's say this is some mu. Okay. Now this is going to be 1 upon sigma. Okay, from here 1 upon sigma under root 2 pi e to the power minus 1 upon 2 x1 minus m. Let's say we are taking this as some mu. Okay. Divided by sigma square times 1 upon sigma. Can you mute yourself? So this is going to be 1 upon sigma under root 2 pi e to the power minus 1 upon 2 xn minus mu upon sigma whole square. Okay. And here we have 1 upon sigma, this term. Now we'll have to do the product. Okay. So since 1 upon under root 2 pi is going to be a constant, what will I get? You will get sigma to the power n, sigma naught under root 2 pi to the power n, right? And in the numerator term, you are going to have e to the power minus 1 upon 2 m minus mu naught upon sigma naught whole square plus x1 minus mu upon sigma whole square plus up to xn minus mu upon sigma whole square. Okay, so can we write it in normal, somehow in normal form?
If we take sigma naught and sigma raised to n together as some sigma parameter, and
Yes, ma'am. We can add over.
Hmm.
We are getting sigma as sigma naught into sigma.
Can we take log kind of thing possible? No.
No, log. We don't really have to take log here.
she's trying to she's asking that can we find out some parameters by which we can convert these as a normal distribution, some mu and sigma with some value.
So what you're going to get is somehow a normal form. Mm.
Ma'am, we can write it separately, ma'am. X minus mu naught and x minus mu. E to the power.
Right. So we have
Just 1 by 2 x1 minus mu square till xn minus mu square into E.
Yeah.
Mu minus mu square E into x minus mu square till xn minus mu square multiplied by E minus mu minus mu naught square upon 2 sigma naught square.
Wait, just take a minute. I will also try to solve this. You can also try it on your own, okay? Just take a minute.
You can separate this x part and mu minus mu naught part.
We can separate this. Yes, we can separate that part.
Yes, ma'am.
Yeah. So we are going to get. Okay, so this you are going to get it as. Okay, so since this is just a constant part, right? This is just a constant part. We can actually neglect this. So we'll be left with e to the power minus 1 upon 2 sigma naught square mu minus mu naught square whole square times e to the power minus 1 upon 2 sigma square. You'll have sum over xi. Okay, this is square, right? So you're going to get you're going to get okay, this sum over xi minus mu whole square, I varying from 1 to n, something like this.
Yes.
Okay.
Yes, ma'am, it is correct.
Yeah, but you have to find, you have to check this posterior is normal. So to check it is normal, it should be something of the form e to the power
Ma'am,
minus
this
1 by 2.
this part is constant, I think, e to the power mu minus mu naught square.
Mu minus okay. Okay, here you'll have to look for this mu bar, sigma bar.
Ma'am, what form, like normal, what form we have to bring in, ma'am, so that I can try?
Yeah, so basically you have to bring this in the form of something e to the power minus 1 upon 2, right? This, the random variable is mu, so mu minus some mean you want, okay? So say I'm writing it as a, okay? Divided by some variance of mu, so let's write it as sigma, this whole square. So you need to bring it to, like, what you need to find, what is your a, what is your sigma.
Okay.
Not
Okay,
just
just
it as b. So what is your a and what is your b? You have to find it from here.
Okay.
It should be doable, but it's a little complicated. Okay, let's try it out later. So I will just write down the result here. We'll do it later, the derivation part. We'll write down the result. So the posterior density, the posterior mean that you get is
Ma'am, we are estimating mu here.
we are estimating mu here.
Yeah.
So the posterior mean, you can try it out. Even in the lecture, it is given as an exercise for you to try. We'll do it later. So the posterior mean that you'll get is x bar n sigma naught square divided by n sigma naught square plus sigma square plus mu naught sigma naught square divided by n sigma naught square plus sigma square. This is correct.
Ma'am, sigma, not sigma naught.
Oh, sorry.
Sigma square. Mu naught sigma.
Numerator, right? It is sigma. So this is the posterior mean that we will get. So mean should basically, so in the expression that we had written, that the posterior density should be of the form e to the power minus 1 by 2 mu minus some a divided by some b square. So this is going to be your a. That we'll have to figure out how do you get this. Okay, so we can try it later, the derivation part.
Yes, ma'am.
Yeah. Okay, then later you had so till lecture 3 we are doing the same thing. We are taking different samples from different distribution and we are different priors, and we're trying to find the posterior mean, posterior distribution, and all that. So it's better now we go back to the problems. So do you have any doubt? Like if you try to solve any problem, can you let me know?
Ma'am, activity 2, 4th and 5th one.
Activity question 10.2, is it?
Yeah, 10.2.
Okay.
4th and 5th I couldn't solve.
Question number 4.
I mean, I got it wrong actually. Not 4th, 5th and 6th, sorry, not 4th and 5th, 5th and 6th.
5th and 6th.
It is based on this only normal thing. It is just substitution, but I don't know how I missed it up.
Okay. So question number 5 here. It says consider 5 IID samples. So the samples are, the sample is 2.5, 4, 6.5, 4.5, and 3.5. And the sample is coming from a normal distribution with mean m, which is a random variable, and sigma 1. Find the posterior mean of m. So you have to find posterior mean of m, where the prior is normal 10, 2 square. Okay. So just now we saw what is the formula for posterior mean of m. Okay. So the posterior mean came out to be, let's say, okay. So what was the posterior mean? It was coming to be x bar
in sigma naught square.
Sigma naught square divided by
in sigma naught square plus sigma square
plus sigma square plus
mu naught
sigma
square divided by
n
sigma
sigma
naught
naught square plus sigma square, right?
Yeah.
So you just have to put the formula here. The calculation is the only thing that you have to do here. So you have the sample given to you. You find the sample mean. Okay.
Yeah.
You know n is 5 here.
Yeah.
What is sigma naught square here?
1.
1. No, it is not 1, right?
Oh, I'm doing the. I think I'm messing it up over there. Okay, it should be 2.
Yeah, it is
4 actually. Yeah.
Now you should be able to do it. So mu naught is 10.
Yeah, it is 10 and sigma is 1. Sigma square is 1. Okay. Okay. I think I'm doing it wrong over there only.
Yeah,
Thank
you
you
should be able to do it.
Yeah, thanks. I think 6 is also the same. I'm doing the same mistake.
Same issue.
Yeah,
Okay.
thank you.
Yeah. Okay. Any other problem that you tried? Anyone? Anyone who has tried the problems? Nobody? Okay, so if none of you have tried, what we'll do is, like, I will tell you to solve some specific problems here. Wait. So just now we saw like if the samples are coming from a binomial distribution, and if the prior is given as some Bitter distribution, then what is going to be the posterior? Now I will give you one problem. So I would want you to try this question. Let's say the problem is the samples are coming from geometric P distribution, okay? And we have taken the prior P, the distribution of this is uniform 0, 1. So you have to find the posterior distribution. Can you try it now?
Yes, ma'am.
Yes, ma'am.
I will give you some 2-3 minutes, then we'll look at it. Okay. Okay, so the one answer that we got for posterior is, it is Bitter n plus 1, comma, sum over xi, I from 1 to n, minus n plus 1. Okay, So this is one answer that we have got. Anybody else who solved? Anybody else who solved?
Ma'am, I got n plus 1 as the second parameter.
You got n plus 1 as a second. So your answer is beta. What is the first parameter?
Alpha is sum over xi, I 1 to n.
Okay.
Minus n plus 1.
Okay.
This is alpha.
Okay.
And
beta is n plus 1.
No, ma'am, no. This is beta, right? This is beta.
Okay.
And alpha is n plus 1.
Okay, so you're getting the same as this.
Yes. I actually got confused.
Okay. Any other answers? No? Nobody tried? If you are still trying, you can let me know. Okay, for the people who have solved this, you can try this one. X1 to Xn, if they are coming from a Poisson distribution and the prior of this lambda is a gamma distribution with the parameter AB. What is the posterior? So you have to, yeah.
Ma'am, I started this way. Posterior is directly proportional to likelihood into prior.
Okay.
Then prior is 1 because it's uniform 0, 1.
Yeah.
And likelihood is Px is equal to x1 till xn given P is equal to P. Okay.
Yes.
But ma'am, this geometric P is for when we are getting the success in the kth trial.
Yes.
So I am not able to write it in this form, ma'am. How we will use this information in writing P is equal to x is equal to x1 till xn?
So how would you write this thing, the probability, the PMF of geometric distribution?
1 minus P.
If we get the trial in the first trial, in success in the first trial, then the probability is P. In the second trial, then the probability is 1 minus P into P.
Yes.
In this way, ma'am.
Yes. So we say that fx of x is P to the probability that x equal k equal P to the power some k 1 minus P to the power
k minus 1. No, ma'am. 1 minus P to the power k minus 1 into P.
Yes.
Oh, yes.
So this is how we write this.
Yes, ma'am.
Okay. Let's say it here only.
So the success is getting 1, I think.
Okay. So the likelihood part, this is probability x1 equal x1 up to xn equal xn, given that this p equal to some small p.
Yeah.
So you're going to get this as so 1 minus p to the power some okay. So saying that x1 is taking the value x1, I mean you're getting the success in the x1 trial, right?
Yes, ma'am.
So x1 minus 1 times p to the power x1.
Why x1, ma'am? Then in the next time I'm getting success. So x minus 1 time I'm getting a failure. So why you are putting x1 there on the p?
Yes, saying that your p, okay, sorry, x1 is taking the value small x1. It means you are getting the first success on x1 trial. You are getting the first success on the x1 trial, right? So this, if you write fx probability x equal k, this we write it as 1 minus p. So for the first k minus 1 trial, you're getting the failure, and for
Yes,
the k trial, you're getting the this
yes,
thing.
so we are multiplying it by p. In the kth trial we are getting success, so the probability of getting success is only one time, that is on the kth trial, and till k minus 1 we are getting failure. So we are multiplying the probability of failure k minus 1 times.
Yes. Here it should not be. Here it should not be x1, right? It is just p.
Yes, ma'am.
Now, similarly, we'll write for everything. So like all the samples. So it is going to be 1 minus p to the power x2 minus 1, right, into p.
Yes.
And is going to be 1 minus p to the power xn minus 1 into p. So this p is occurring n times. So I can write p to the power n and 1 minus p to the power x1 plus x2 plus up to xn.
Yes, ma'am.
Minus of n.
And
this is what our likelihood is. And the prior was just 1.
Yes,
so this is again something of the form beta, right? Even this is together. So this is again a beta distribution where we are saying okay. So
alpha is n plus 1.
Yeah. N plus 1.
And beta is
going to be
x1 to xn minus
yes
minus n plus 1
plus 1, right?
Yes.
This is clear?
Yes, ma'am. Ma'am, but what is success here, ma'am?
Success. What is success here? That is, I mean, that is not defined. We're just saying that the probability of getting a success is p.
At this point, I got stuck, ma'am. I thought getting 1 is a success, so I couldn't imagine how.
So, like when we write the PMF for a geometric distribution, so we say like x is a geometric distribution, and saying that the probability your x random variable is taking the value k. So saying that p equal x equal to k. So what does it mean? So basically it means what is the probability that you are getting the first success, whatever success is, you are just getting the first success on the kth trial, right? This is what it means. And we write this probability as 1 minus p to the power k minus 1, that on the first k minus 1 trial you're getting 1 minus p, and on the kth trial you're getting the success. So similarly here, you know, these samples are random and they're independent. the ID samples. So you can just multiply, right? This is what we have done. So probability that x1 equal x1 given p equal p. So this x1, capital X1 is a random variable and it is taking the value small x1. So
yes, ma'am.
We are trying to say that the random what is the probability that your x1, capital X1, is taking the first success on the small x1 trial. So it means on the small x1 trial, you are getting the first success. It means before, like till x1 minus 1 at trial, you should have a failure.
Yes, ma'am.
So it is going to be 1 minus p to the power x1 minus 1 times p. Similarly, 1 minus p, p x2, 1 minus p to the power x2 minus 1 times p, and so on.
Okay, ma'am, got it.
Yeah.
Yeah.
Okay, so this was about when the samples are coming from geometric distribution and the prior was uniform 0, 1. Then we got the posterior to be again a beta distribution with the parameter A to be n plus 1 and the parameter B to be sum over xi minus n plus 1. Now, the second question that I've given is, if the samples are coming from a Poisson lambda distribution, and if the prior is a gamma, if the prior of this lambda is a gamma distribution with the parameter A comma B, what is going to be the posterior distribution? Okay, so Kavita has already given the answer to me. So I will just wait for 2 more minutes. Let others also solve it and then we will move. Okay.
Ma'am, how to find that sequence, some of the sequence, ma'am, that Poisson sequence? Do we need to derive formula or something we have to calculate, like something?
I did not understand what you're trying to say.
Ma'am, actually, for this question, okay, Poisson. So to find the likelihood function, which is a Poisson thing, right? Okay, so which is like, so formula is like I think e की power of minus lambda and this thing, right? So we have to multiply all this variable, right?
Yeah, you have to multiply.
Yeah, so they will become a sequence, isn't it?
Yes.
So do we need to take the sum? I mean, how to take this, like the sum of that sequence actually? That there actually I'm getting stuck.
Okay. So. All right, so you have x1 to xn from Poisson lambda, and we are saying this has the distribution gamma AB. So the posterior is prior times likelihood. Right? So what is the prior distribution?
I mean, this will be gamma thing, right?
Yeah. Gamma. So what is the PDF?
X की power a minus 1.
Yeah. X to the power a minus 1, e to the power minus bx.
Yeah.
So here in place of x, we have lambda, right? So just write lambda here. Okay. So lambda to the power a minus 1, e to the power minus b lambda. Now we have likelihood. So, you know, likelihood is given by, I mean, the distribution Pmf of Poisson is given by e to the power minus lambda, lambda to the power x upon x factorial, right? So here it is going to be e to the power minus lambda, lambda to the power x1 upon x1 factorial times e to the power minus lambda, lambda to the power x2 upon x2 factorial times e to the power minus lambda, lambda to the power xn upon xn factorial. So you know this x1 factorial, x2 factorial, xn factorial, all are going to be constant. So I can just neglect this term. And we will have lambda to the power a minus 1 e to the power minus b lambda. And we'll have e to the power, you can take minus lambda to be constant, right? I mean, common.
Yes.
And basically it is going to get multiplied n times. So it becomes e to the power minus n lambda, right? So it becomes e to the power minus n lambda, and lambda to the power x1 plus lambda into lambda to the power x2 up to lambda to the power xn. So this becomes lambda to the power sum over xi, right?
Yes, ma'am. Yes, ma'am. I think I did mistake. Yeah.
Now you can write this as lambda to the power a minus 1 plus sum over xi and e to the power minus of lambda n plus b. So again, can you figure out how does this distribution looks like? Can you identify it?
This is gamma, ma'am. Gamma only.
Yes,
No,
this is gamma only. Gamma only.
This is a conjugate distribution then?
Yes, the prior is conjugate. So the gamma prior is a conjugate prior for this Poisson lambda. Okay. So what is A here? What is the parameter alpha?
A plus sigma, I think.
A plus
summation of
sum
xi.
over xi, no?
Yes, ma'am. Yes, ma'am.
A plus
And what is the parameter beta?
minus n
Plus
plus
1.
b.
N plus b actually.
It's just n plus b.
Okay, yes.
Yeah. So this is what you have. This is the posterior. This is the posterior distribution of. What is the posterior distribution of? Can you tell me? This is the posterior distribution for what?
Lambda.
Lambda, right?
Yeah.
Now, if I want to find the estimator for this lambda, so I know the posterior distribution. So I'm going to find the estimator posterior mean. And what is this going to be? Alpha by beta, right? If you have a gamma distribution, then
Yes, ma'am.
mean is given by alpha beta. So here it is a plus sum over xi divided by a plus sum over xi plus n plus b, right? This is going to be posterior mean. So first you should learn like how to find the posterior, right? So there are many examples given in the lectures also. There are many examples given in the tutorial problems, activity questions. I would suggest you all to like go through it and try to solve different problems. It's not difficult. The same method you'll have to use. Okay.
Ma'am, could you explain me about that factorial in the denominator? X1 factorial, X2 factorial.
So see this, what is this x1 factorial? So this x1 is a sample, right? X1 is the realization of a random variable x1. So you know this x1 is a constant, right? This x1 is going to be constant. I mean x1 factorial, x2 factorial, x3 factorial. All these are going to be a constant.
Okay, ma'am.
Right?
Yeah.
So we can neglect this. Mean is correct. Okay, is it? Oh, okay, right. Mean is not correct. Yeah, thanks. So it is not okay. This was a gamma distribution, right? Not beta distribution. So the mean that you will get is alpha by beta. So a plus sum over xi divided by n plus b. Yeah, thanks Kevin for the correction. I hope this is correct now. Okay. So anything in general you want to ask from week 10?
Ma'am, still have to complete some of the parts, so not at this time from my side.
Yeah, so whatever we discussed today, right? So just try to solve many problems. So there are many problems in tutorial and activity questions. So you can try those problems. The method that you're going to use is exactly the same. And like different samples coming from different distribution, you're taking different trials and you're trying to find the estimator.
Yes, ma'am.
Yeah. So,
ma'am, a question, ma'am. Hello.
Yes.
Ma'am, this is, more to do with how to cope with week 10. I'm yet to do week 9. I mean, how important is our week 9 concepts for week 10? Like, can I skip week 9 and go to week 10 directly, or do I need to complete week 9 first and then go to week 10?
I would suggest you finish week 9 first and then come to week 10. Because even in week 10, you are going to use the concept that is being taught in week 9.
Okay, ma'am. Ma'am, and any suggestions or tips how to like get it done 2 weeks of material in this short time?
Okay. So in week 9, basically you have two different ways to design the estimator, that is method of moment and maximum likelihood. So I would suggest just go through what is the basic idea, like what exactly are we doing in week 8. Like we are trying to estimate the parameter. Just try to read the theory part, and then you can do the estimation part, like how are we designing the estimators there. So you can look at method of moment and maximum likelihood. So these two methods these two are the frequentest approach to design the estimator. And in week 10 we are just like looking at how are we going to how are we going to design the estimator through Bayesian approach. So that you can do, I think.
Okay, ma'am. That's basically week 9.6, 7, and 8 mostly, is it?
Sorry, week
9.6, 7, and 9.6, 9.7, and 9.8.
No, I would suggest you also read some theory like that is given in the first 2 lectures. It is important. Like understanding the theory is important. So sir has explained it in a very nice way. So I would suggest you watch at least the first 2 lectures of week 9. And there are some concepts. Yeah. Okay.
And you're saying, ma'am, you're saying something, and there are some.
So there are few things also that was introduced, like how do you check the biasness. So that is important to read in week 9. So at least for this course, you can read the biasness also and the design of estimators. Okay.
Oh, okay, ma'am. Thank you so much.
Yeah. Okay, so let's close the session for today. I would suggest you all to solve few problems. So we'll meet again on Sunday. This Sunday. Sunday is it? No, Friday.
Okay, ma'am. Thank you.
Yeah. Thank you all for joining the session.
Thank you, ma'am.
Thank you.